All right, welcome to MAC 2013 Calculus 3 Final Exam Review. So for today, and then also our next and final class on Wednesday, I'll be going over the spring of 2018 final exam that's been posted on Canvas. So that'll be what I'm doing for the next two classes here. So as a reminder, the final exam is not cumulative. It's going to be over lessons 27 through, I think it's 27. Yeah, 27 through 34. Although even though it's not technically cumulative, we're definitely going to need to pull out all the stops for this one. We're going to be doing double integrals. We're going to be doing triple integrals. We're going to need to know about vectors. So even though it's not cumulative, technically, we're not going to just give you a random triple integral or a random vector thing to compute. We'll definitely need to have all of that knowledge, because the last section kind of combined everything together. I misinformed you guys last class. So this sheet right here, the summary of integration formulas with all the various versions of the fundamental theorem of calculus, all of these will be provided to you on the final exam. So you do get the list, all of what you're seeing right here. You get all of this. I mean, I don't know how much this will be useful directly, but you're definitely going to want to use all of these probably at least once on the exam. Well, I guess I'm not going to guarantee that, but you will probably end up using all of these at least once on there. It's going to be uploaded on the actual exam, so it'll be on there. All right. So with that being said, let's kind of keep this in the background. Let's remember that we have it, and let's go ahead and go over the exam here. All right, so let's get started. So suppose we have a vector field f of x, y, z, and it's this vector field here. Find the curl of f at 1, 2, -1. All right, well, let's see. So what is the curl? The curl of f, actually, this is my bad pen. The curl of f is the del operator cross with the vector field itself. Or in other words, we have a cross product, I, j, and k. We have partial derivatives here with respect to each variable. And then we have our vector field itself. All right, which test is this again? Spring of 2018. Okay. So let's see here. So let's go ahead and take the cross product here. So we have the y derivative of this, which will be 2xy. And then we subtract, and then we have the z derivative of this, which is x squared. All right. Let's see, we have j here. So we do the x derivative of y squared. Well, actually, the x derivative is y squared. And then we do the z derivative, which is 2yz. So we have 2yz minus x squared, or y squared, excuse me. And we put these in the reverse order because it's j hat. And then with k hat, we have the x derivative of this, which is 2xz. And then we have the y derivative of this, which is z squared. All righty, there we go. So now all we need to do, so this is the curl of f, which is a vector field in its own right. And what are we supposed to do? We're supposed to plug in the points x is 1, y is 2, z is -1, and see what we get. So we're doing this at 1, 2, -1. All right, let's see. 2 times 1 times 2 is 4, minus 1 squared will be 3. Okay, so I guess we can eliminate that choice. We have 2yz. So it's going to be -4. And then we subtract y squared, which is another 4. So we have -8. And then finally, we have 2xz, which is -2 minus z squared, which is subtracting another 1. End up having -3 here. So D ends up being our answer for this one right here. All right, so there we go. And remember the curl, so what does this represent? This 3, -8, -3? The vector is pointing along the axis about which you're curling. So if you did the right-hand rule on this vector field, your thumb would be pointing in the direction of this vector. And then the greater the magnitude of this, the more kind of curly it is going around a particular point. All right, next question here. Which of the following vector fields are conservative on their respective given regions? All right, so we have negative yx on R2. Well, let's see here. Let's do the cross partials of this. So we have q sub x, the x derivative of this is 1. And then we have p sub y, which is negative 1. All right, well, these need to be equal if it's a conservative vector field, so that's definitely not. All right, let's take a look at G here. So for this one, q sub x is 1 over x. And p sub y, I do the y derivative of this, and I have 1 over x. All right, these are the same, but remember, those being the same is not necessarily going to give us a conservative vector field unless this is a simply connected domain here. But this is just going to be a box. This is going to be all x greater than 1, y greater than negative 1. So this domain will look like this here. And that's going to be simply connected. There aren't any holes in here or anything like that. So yes, G actually will be a conservative vector field here. All right. And then finally, we have y e to the xy and then x e to the xy. That's almost a tongue twister. All right, and this is on the whole of R2. So this should definitely be okay here. All right, so we do the y derivative of this, and we get xy e to the xy. And then we do the x derivative on this and get xy e to the xy. All right, so these are the same. And then on the whole of R2, this is going to be conservative because this is another simply connected domain here. So it turns out that G and H are going to be our conservative vector fields here. All right. Remember, it's really nice when something's a conservative vector field. Okay, next up here. Oops, that's not next up. This is next up. All right. Let's go down here. The figure shows a vector field F and two curves C1 and C2. Which of the following is correct right here? Okay, well, let's see here. So all of these integrals here are measuring F dot dr. So what does that mean? It's roughly measuring how much the vector field is going in the same direction as the curve. So if the vector field is pointing along the direction of the curve, that'll count positively. If it's kind of perpendicular to the curve, then it'll be 0 or neutral. And if it's pointing backwards along the curve, it'll count as negative. So let's follow along C1 here. So if we look at the arrows that we're encountering along C1, they're not 100% pointing along the path, but they definitely seem to mostly be pointing along the path here. So we should definitely get some positive value of F dot dr from this. So we can eliminate, say, like this answer right here. All right, and then let's go ahead and follow C2. Let's see what happens with that. C2 looks like we get maybe some zeros around here. This looks perpendicular, but then we start getting a little bit of negatives here because these arrows are pointing in the opposite direction to which we're going, but they're still mostly perpendicular. And then we're definitely getting some opposing directions. This one's really opposing right here. So what do you guys think the sign of this integral going along here will be? That's right. It's going to be negative because we either have things maybe contributing close to 0 and we have a little negative and then we have big negative. So all together, that's going to be negative. So we see right here that the integral is negative and it's less than this one right here. We wouldn't pick this one because that would mean it's positive. We already eliminated that one. And this one's saying it's positive as well. So it's going to be this guy right here. All right. If it's perpendicular, why is it 0 again? Well, if you have two perpendicular vectors and you dot them together, you get 0. So that's why it would be 0. All righty, so we got that one. Yeah, the integral along C2 is negative because the arrows are pointing in the opposite direction that we're traveling here. All right, next up, let S be part of the cone square root of 2x squared plus 2y squared. Right, wait, we missed 4? Oh, we did miss 4. Sorry, 4. All right. Suppose f of xy is negative yx. Let C1, C2, and C3 be linear paths respectively parametrized by these parametric equations for t going from 0 to 1. Now, if C is the union of all these curves, meaning we travel along all 3 of them, then evaluate the line integral f dot dr. Okay, now anytime there's something I need to integrate that's going to have a bunch of components to it, I don't want to do that. I want to find a way around that so I don't have to do 3 separate integrals for this. So then I'm going to keep my my formula sheet kind of in the background here. I'm going to try to see if I can maybe use something on this to help me out here. But first of all, I should probably try to get a glimpse as to what this region looks like. That would probably help. All right, so for t equals 0, I plug that into the first region and I get 0, 0. And then when we go all the way to t is 1, we get up to 2, 2. Let's say that's right here. Okay, so we're going that way. Next, if I plug 0 into here, I'm going to start at 2, 2. And then I'm going to go to t equals 1, which will be 2 minus 4 is negative 2 for x and 2 for y. So my next path just is this straight path across to x equals negative 2 right here. All right, and then finally we plug in 0 for this and get negative 2, 2 as expected. So we're starting from the same place. And then we go plug in t equals 1. And as you also might expect, we're going to have negative 2 plus 2 is 0, and 2 minus 2 is 0. So we're back to the start. All right, so it seems like we're integrating along a closed path. And it seems like it's a positively oriented closed path, because at all times our area is going to be to the left here. All right. So let's see here. So while I could substitute in these into here and do 3 separate line integrals, like I said, I don't really want to do that, right? What I instead want to do, oh, I guess it's not on here. This is actually missing one from the one we had in class. I'm going to use the Green's theorem that's specific to 2 dimensions, because we only have a 2-dimensional vector field right here. So this theorem, another version of Green's theorem, says that the double integral of qx minus py dA is the integral along the closed curve of f dot dr. So remember, this is the one that's specific for f having just 2 components like that. All right, how do I know which direction it is? Remember, the orientation is positive if I'm walking along my path here and the area is always to my left, which it is in this case. So this is positively oriented. All right. Let's see here. So now that we have this, is it going to be added to the sheet? I'm not sure. If it isn't, remember that you can imagine a 2D vector field as this: the component for x, the component for y, and 0. And you could do the curl of this, and you end up with this one right here. So this kind of comes for free along this one right here. How was R2 plotted? I plug in 0 for this, and I start at the point 2, 2, which is right here. And then I go to t equals 1. I have 2 minus 4 is negative 2, which is right here. And then 2 for y right here. What if it were given reversed? Would we just negate the final answer? Absolutely. Yes. If we have negative orientation, we just do everything for positive orientation and then stick a negative at the end. All right. Anyways, let's see how we would actually do this. So let's go ahead and use Green's theorem here. So if we want to do this line integral, instead of doing the line integral, we could do a double integral of qx minus py. Now this is p and this is q, right? So let's see what the double integral over this domain of qx minus py is. Okay, well, py is -1. QX is 1. So it seems like QX minus PY is actually just 2. Okay, so we have the double integral of 2dA, and more notably, this is 2 times the double integral over our region of 1dA. And what geometric quantity does this represent right here? What is that? It's the area, that's right. So we simply have to find the area of this region, which will not be difficult because it's a triangle, and then we could just put that in for this. All right, so it seems like the base of our triangle is 4. The height of our triangle is 2. So this will be 2, and then we have 1/2 base times height. So we end up with 8. And that's going to be our answer right here. So remember, the moral of the story is just because you can do something, just because we could have plugged in these parameterizations and done our line integral manually, does not mean it is right to do so, or it's good to do so. So if you ever see something split up into a bunch of components, see if you could use one of the equivalent fundamental theorems of calculi. I don't know if that's the right plural, but use one of these guys if you see something with a bunch of components here. How would you do this if QX minus PY isn't constant? Then we would just do the double integral over this region right here. So we would just set up a normal double integral and do that, which in many cases, that's still easier than parameterizing 3 different paths right here. Okay, now we can move on to 5, now that we've given 4 its due here. Let's see right here. How do I get the numbers from the integral of 1dA? It's the area of a triangle. So we have the base here, the height here, and then 1/2 times that. All right, now number 5. Let S be part of the cone. Z is √2x² plus 2y² with 0 less than or equal to z less than or equal to 2. Then the area of the surface S is, all right, well, this means that if we're finding the area of a surface, we are finding surface area, which has a particular formula. This is going to be the double integral of RU cross RV dA right here. So what we need to do is we need to find a parameterization of this surface. Now we have Z given to us as a formula with X and Y. So we could do it that way. There's nothing wrong with doing it that way. But it seems like all of our answers actually have things in terms of polar coordinates. So perhaps we should parameterize the surface in terms of r and theta so we can end up with something that appears in our answer. So what I'm going to do is I'm going to parameterize the surface according to r and theta. All right, let's see here. So it seems like for x is r cosine theta in polar coordinates. Y is r sine of theta. And then z is the square root of 2x² plus y². But in polar coordinates, that's the square root of 2r² or √2r. Now, since z is positive here. So we have √2r for that right here. All right. Will the answer always be double the problem number? I think that's only been true. Has that been true for any of the earlier ones? that was purely for number 4. So that was a coincidence. All right. So back to this. So we now have the parameterization of our surface right here. So now we need to compute RU cross RV, which is going to be R cross R theta. And remember, that's an abusive notation. It's technically bad form to have R here and here, but we know what we're talking about. It's going to be okay. R. Let's see. So I'm going to do the R derivative of all of this. So I have cosine of theta. I have sine of theta. And I do the R derivative of this, which is √2. Next, I have R theta. Let's see, that will be negative r sine of theta, r cosine of theta, and 0. Okay, so I'm going to compute the cross product of these. Here's kind of a cool trick that I use to do cross products to save time. So I would technically have to write out the determinant with all the stuff here, right? But you could also kind of just put little I, J, and K above the two things you're crossing if you write them one on top of the other. So you could almost kind of have your little determinant thing already written like that, and then you could just skip to doing the vector here. Oh, you guys already do that? Yeah, that's what I do to save some time. All right. So I do, for I hat, I do sine times 0 minus root 2 r cosine theta. All right, next, for j, we have cosine times 0 minus the negative of this, so it'll make it positive, but then j hat comes with its own negative. So we end up with that. That seems kind of symmetric, I guess. And then for k hat here, we have cosine theta times r sine of theta. So that's r cosine squared. I think we see where this is going. And then we subtract negative r sine squared. So we have r cosine squared plus r sine squared. But of course, this can be abbreviated as r because this is a Pythagorean pair right here. Okay, so we got that. But remember, we need to find the magnitude of this vector, right? Let's see what that is. Let's see. So it's the square root of each of these squared. So I have 2r squared cosine squared plus 2r squared sine squared plus r squared. We see we have another Pythagorean pair. So this will simplify to 2r squared plus the additional r squared will be 3r squared, which simplifies to root 3r right here. So this is exactly what we're going to put in to our integral right here. All right, so then this will be the double integral of root 3r dr d theta. Now we've already, by figuring that out, we've already narrowed it down to these two here. So now it just comes to figuring out what the bounds are. And it seems like 0 to 2 theta is there no matter what, or sorry, 0 to 2 pi or theta. And then remember, z ranges from 0 to 2, right? So if z is 2, then we divide by root 2 here, and we get that r is root 2. So really the upper bound should be root 2 and not 2 right here. The Jacobian is, I think someone was very astute to notice this earlier. The Jacobian is kind of baked into this already. That's why there's an r right here, because we're effectively just using polar coordinates for this. That's why we get the r right there. All right. Let's see here. Oh, I think if someone else had a good question. See, people have, I think they ask, is RU cross RV called N? And the answer is yes. This is a normal vector, and we'll get to that a little bit later. So you can think of this as N if you want. There's only one that had the square root. No, there were two. There was this one as well. So the difference was figuring out whether the upper bound would be 2 or root 2 here. Oh, it doesn't have an R? Oh, oops. I overlooked that. Okay, yeah, then I guess we could have just stopped here. Whoops. All right. Number 6. Suppose f of x, y, z is a potential function of this vector field. All right, so here's our vector field. Now they say it has a potential function, so I'm not going to go through and check all of the cross partials to see if they're equal, because I'm assuming they're not going to be conniving enough to like say, oh, there's a potential function. Oh, psych, there isn't one. It's not conservative. So I'm going to assume that there is one. If f of 1, 1, 0 is 3, then what is f negative 1, 2, 3 right here? All right, so let's go ahead and figure that out. So first of all, let's figure out what the potential function is for f. And remember how we do that. Remember, this is the x component, the y component, and the z component. And we integrate each component, or actually we call these p, q, and r. So we're going to integrate each component with respect to their matching variable right here. So let's see here. So I'm going to do the integral of the x component, 2x minus z dx. So the integral of this will be x squared minus xz. And then I could potentially have some stuff that involves y and z, because remember, those are constants when we're working with x here. Okay, next, we have the integral of z dy. So this will probably give something that appears in here. So I do this integral, and I end up getting yz, plus potentially some stuff with x's and z's, which is probably that stuff right here. And then finally, just to make sure we're not missing anything, we have the integral of negative x plus y dz right here. So I do the negative, I integrate negative x with respect to z, get negative xz. All right, we already had that. I integrate y with respect to z, I get yz. I already had that. And there could be something involving x and y that we missed. Okay, so looking at this, I need to find every component that appears and include it at least once, or just once. So my f of x, y, and z, let's see, I have an x squared, I have minus xz, and then I have plus yz. And that takes care of every specific term that we ended up getting. Now, remember, we didn't do this quite a lot in class, but remember, potential functions have a plus c. You can almost imagine this plus c is kind of coming from all of these integrals right here. Now, what we're going to do, since we know that f of 1, 1, 0 is 3, we can actually compute what this plus c is. So f of 1, 1, 0. All right, let's see. So that is 1 minus 0 plus 0 plus c is 3. All right, well then naturally that means that c's got to be 2. So now we have our specific potential function. So this is x squared minus xz plus yz plus 2. All right, and then finally, armed with this knowledge here, we can find out what f of negative 1, 2, 3 is. So let's plug that into here. Negative 1 squared is 1. We have minus negative 1 times 3, so it seems like a plus 3. We have y times z, which is 6. And then we add the 2 at the end here. 1 plus 3 plus 6 plus 2 is 12. So that's going to be our answer right here. All right, there we go. So we found the potential function. We found out specifically what the constant is here. And then we plugged in all of our numbers right here. Can I explain how I found the upper bound for r and 5 here? Yeah, sure. So I know that my z is limited between 0 to 2, right? So at the very biggest for z, I know that z is going to be 2. But remember that z is root 2r. We figured that out in the beginning. So I'm going to divide by a root 2, and I get that r is root 2 when z is at its biggest at 2. So I know that my biggest for r will be root 2 here. Can I show the integral identity on the sheet with the magnitude of RU and RV? No, because it's not on there. Anytime we have to do with something with a ds, anytime there's something with a ds in there, that's going to include RU cross RV, more likely than not. All right, let me make sure I don't skip any other ones. All right, 7. Let's take a look at that. All right, so this is a 2-part question. This is going to apply for 7 and 8. Consider the surface S parameterized by r of uv is 3 cosine of u, v, and then sine of u, where u can range from 0 to 2 pi, and v can go from -1 to 1. Identify what the surface is. Okay, so first of all, I see a sine cosine pair in here, right? Whenever we have a sine cosine pair for a parameterization, it means it's going to be a circle in whatever plane that is. So since we have it for x and z, there's going to be a circle, or I guess actually in this case, it's going to be an ellipse since this is a different number than that. We're going to have an ellipse in the xz plane. So here's our three-dimensional coordinate system. Here's the ellipse, and extends 3 in the x direction, 1 in the z direction, right here. All right, yeah, it's an ellipse because this is a different number than the coefficient right here. So it's going to stretch out more in the x direction. And then whatever the other one is, so we have a different variable here, v, this is going to be how much the ellipse extends in the remaining direction. So we already used x and z. So our cylinder is going to extend in the y direction. And what's the range for the variable for y, which is v? It's from -1 to 1. So it's going to extend out to y equals 1. So it's going to extend out this way a bit. And then it's also going to extend backwards to -1. So it'll look like that. So it's this cylinder here. Now remember, this isn't technically like the cylinder you learn about in elementary school where it's a circle that's stretched out. Remember, we have the more general definition of cylinder in this class where it's a 2D shape kind of stretched along an axis here. So you could almost think of this as like an elliptic cylinder or something like that, but it's a cylinder nonetheless. All right, so we got that. Would an elliptic paraboloid be if y was v squared instead of v? Actually, no, it wouldn't be that. It would actually just be half of this cylinder. Because if y was v squared, then v going from -1 to 1 would mean that v squared would only go from 0 to 1. So it would actually still be a cylinder. It would just only be this half of it right here. All right. So v is what makes it a cylinder? Kind of. It's having some kind of shape in 2 of the dimensions and then just stretching it out linearly in the 3rd dimension. That's what makes a cylinder. All right, so we answered that. So we know we're dealing with some kind of cylinder for this surface. All right, now suppose if n hat is the unit normal vector with non-negative z component to the surface S at r pi over 4, 0, then which of the following vectors is in the same direction as n hat? Okay, now this is where we're going to come back to what I was talking about earlier with the RU cross RV. What did I write? Oh, it was on the other side of this page. Yeah, so remember someone asked here, and they were very perceptive to notice this. RU cross RV is a normal vector. So that's exactly how we're going to get our normal vector in this problem. We're going to compute RU cross RV at this point right here. Can we just have a square cylinder, or is that just a cube? Yeah, it's both. It's a square cylinder and a cube. Yeah, so all cubes are technically cylinders, according to this definition. All right. So back to this one though. Let's go ahead and compute RU cross RV, because that will get us the direction of our normal vector. So RU right here, let's see. So the U derivative of all of this will be -3 sine of u, 0, and then cosine of u. Let's see what RV is. RV, well, that's even easier to compute because it's going to be 0 right here, 1 right here, and 0 right there. Okay, so remember our normal vector will be RU cross RV right here. Okay, well, I'm going to do my cross product trick to save a step here. I'm going to stick I, J, and K on top of these right here. So for my I coordinate, I have 0 times 0 minus cosine times 1. So it's going to be negative cosine of u. For my J component, I have -3 sine of u times 0 minus cosine times 0. Okay, so that's just going to be 0. And then for my final component, I have -3 sine of u times 1 minus 0. Okay, so there we go. So this is a normal vector, but remember, we want a normal vector with non-negative z component, right? Now, if I plug in u is pi over 4 and v is 0, the z component of this will be negative because it'll be -3 and then √2 over 2. So this isn't quite the one I want. the normal vector I really want that we're actually going to use is the negated version of this. So I have cosine of u 0 and 3 sine of u. And the reason why we're using this is it has a positive z component, because that's what they wanted here for our unit vector here. How did I get RU and RV again? I took the u derivative of this, and then I took the v derivative of this up here. Okay, so this is going to be the normal vector that I'm going to be using. Now let's go ahead and plug in u0 right here. So our normal vector will be root 2 over 2, 0, and 3 root 2 over 2. Okay, but the main thing to get out of this is we don't actually need the specific vector here. We just want the proportions of the vector, because we want something in the same direction as n hat. And this isn't even n hat, this is n. It's stretched a little bit. But all right, so it seems like we have 0 for our y component, but that doesn't narrow it down because we have 0 for all of these y components. But then it seems like the z component is 3 times as large as the x component. And it seems like there's only one of those that does that. It's going to be this one right here, option D right here. So that's going to be our pick for this. So we found something parallel to the normal vector, and it has the same proportions right here. All right, wonderful. So that's number 8. Let's go to number 9. Let's see. How is that parallel? It's a multiple of the vector. Yeah, so if I multiply this by root 2 over 2, then I'm going to get that one right there. All right, suppose that we have this vector field, xy squared, yz squared, zx squared. That seems pretty symmetric. And let S be the union of the upper hemisphere of radius 2, centered at the origin, with the disk of radius 2 in the xy plane centered at the origin, such that S is positively oriented. Evaluate the surface integral of f dot ds. Okay, so I am seeing some, what was I saying? Yeah, I'm seeing more than one component for this. So I'm tempted to see if I can use one of these integral formulas here. All right, so let's see what we have going on. So we have our upper hemisphere like that, and we're also including the base as well. So we have this closed surface right here. We want to do the surface integral. I don't know how bad it would be to actually do this. It would probably be kind of nasty. We'd probably have to do some nasty trig stuff. So I don't really want to do that. Let's take a look at our handy dandy sheet here and see if there's something we can do. All right. Let me just cover this up for a second. So let's see. Fundamental theorem of calculus. We're not in Calc 1 anymore. We're not going to use that. We don't have anything looking quite like this. We have more than just a line integral. What we're trying to do here is we're trying to do a surface integral. We're trying to do this right here. Now this says that if I have a surface integral, and I guess this should really have a circle there. If I'm doing the surface integral on a closed boundary around some kind of volume, then instead of doing that, I can instead do the triple integral of the divergence of f. And I do the triple integral in that region right here. All right, so rather than doing the surface integral, which in all likelihood will be really annoying, it'll have a bunch of trig functions in it, I'm instead going to do the triple integral of the divergence. Let's see if that works out. The divergence of f. All right, well, what is the divergence of f? Let's see here. So remember, the divergence is where we do the x derivative of the x component, the y derivative of the y component, and the z derivative of the z component. All right, the x derivative here is y squared. The y derivative here is z squared. And then the z derivative here is x squared. Okay, now think about this. So we're doing this triple integral. We have x squared plus y squared plus z squared, and we're integrating over half of a sphere. So what coordinate system do you think we should use to do this problem? Yeah, we should definitely do spherical coordinates for this. Yeah, hands down. All right, especially because what is this going to be in terms of spherical coordinates? Rho squared, that's right. All right, so we're doing our triple integral and we get a rho squared from this. And then our Jacobian for using spherical coordinates is rho squared sine of phi. D rho, d phi, d theta. Okay, now let's figure out what our bounds are going to be in terms of these new coordinates. Rho, so this is a sphere of radius 2, right? So we're definitely going to go from 0 to 2 for this. Phi, we can start by being perfectly vertical and then come all the way down until we get to the z equals 0 plane. So that's going to be a phi value of pi over 2. And then it seems like we could spin all the way around the sphere this way. So that's 0 to 2 pi. All right, so this can split over multiplication. We have all constant bounds, so we can do our lovely multiplication trick here. So it's the integral from 0 to 2 pi of d theta, the integral from 0 to pi over 2 of sine of phi d phi, and the integral from 0 to 2 of rho to the 4th d rho. Okay, why are the bounds constant and not in terms of each other? Because it's a sphere. The sphere kind of naturally is the nicest thing or the easiest thing to express in spherical coordinates. If you have a sphere as your bound in spherical coordinates, then all of your bounds will be constant. All right. So let's see here. Can you do half of the sphere volume formula? Well, we're not just integrating dv here, we're integrating rho squared. So it's a bit more complicated than that. If we were doing the triple integral of 1 dv, then yeah, we could have done just the volume of the sphere. How's that integral different from not including the bottom disk? We couldn't use the divergence theorem if we didn't include the bottom disk, because then we wouldn't be enclosing a volume. And it's funny that you mentioned that, because there's actually a problem a little bit later that looks like you could use the divergence theorem, but you can't. All right, anyways, let's finish this here. We have the integral from 0 to 2 pi of this is 2 pi. The integral from 0 to pi over 2 of sine, well, let's see, this becomes negative cosine. Negative cosine of pi over 2 is 0, minus negative cosine of 0. All right, so that's just 1. And then this will be rho to the 5th over 5, 32 to the 5th power is 32. So we end up with 64 pi over 5, which is one of the answer choices right here. All right, wonderful. All right, so we got that one. And once again, we had some of our integration formulas coming to the rescue. We might have been able to attempt this as just a straight up surface integral. We would have had to do 2 of them because we would have also had to parameterize our bottom one here. So yeah, it's not really something you want to do here. All right, let's go to this next one. Which of the following regions is /R simply connected on R2? All right. Why is there no n hat is the question, like, is there on the formula sheet? Oh, so remember that n hat ds is equal to ds with a vector symbol here. So they wrote ds with the vector symbol for this one. And then they had the n hat ds without the vector symbol in the formula sheet, but they're the same thing. All right. Let's see here. So I have p x squared plus y squared less than 1. So this is just the units or everything within the unit circle, not on the boundary. Is this simply connected? Are there any holes in here? Can we constrict every loop down to a point? Yeah, we could do that. Yeah, because like there's no holes in here. Like if I drew like this kind of weird path or whatever, and I like kind of pulled this in towards the starting point, I wouldn't have to jump over any holes. So yes, this one is simply connected. Okay, now the next one's very similar, only that x squared plus y squared combined cannot be 0. So this one is going to be the open unit circle or open unit disk, but then there is a hole at the origin here. So what about then? That's right. Yeah. So we have the hole now. So if I maybe drew like a loop, for example, like let's say I drew this like kind of closed loop like right here. There's no way that I can pull, like if you imagine this as a string, there's no way I can pull all of the string to be concentrated at one point without having to like lift the string up into the third dimension over the hole right here. So this one is not simply connected. All right. And then the final one here, 1 is less than or equal to x squared plus y squared less than or equal to 9. So we're between two circles of radius 1 and 3. But y has to be positive. Let's take a look at that. This is like an open annulus. Well, it's open, so I should draw the dotted lines. So it's going to be like this right here. Okay. So is this simply connected? Can we take any loop that remains completely within this and collapse it to one point? Can we like crunch up all of the string from this loop to one point without having to like jump into the third dimension to do it? That's right. Yes. So this one is simply connected. We end up with P and R. Oh, I guess I kind of spoiled it by putting the answer right there. Let's see. How are we doing on time here? Oh no. Dropped my sheet. All right. I guess we have time for one more here. Let's go ahead. Number 11 right here. If S is the part of the paraboloid, Z equals 4 minus x squared minus y squared with Z greater than or equal to 0, f of x, y, z is negative y, x, z, and n is the upward normal unit normal vector on S, then what is the surface integral of the curl dot n hat ds? Okay, now you could, I don't know if you could see this clearly or not, but when I was doing this, I actually made a mistake on this problem. So I circled 0 because I thought, like I mistakenly believed that this was like the problem number 9, where it not only included the kind of dome here, but it also included the bottom. But it doesn't say anything about including this disk at the bottom here. So I assumed that this would be another surface integral over a closed surface, meaning I could use the divergence theorem. Now, if it were that way, if we did include this bottom, why would the divergence theorem be really nice for this? Why would the divergence theorem be even nicer than the previous problem?
You make it over a curve.
It's not quite like that, because you get 0. That's right. So if we do the divergence of this, we're doing the triple integral of 0. Because remember, the divergence of the curl of anything is 0. That's why I circled 0 immediately, because I was like, oh, it's just a closed region doing a curl surface integral, so it's going to be 0. But it doesn't include, the reason why we can't do that, the reason why I erased this is because we don't include the base right here. All right. So we need to actually do this one manually. So we need to compute the curl. We need to find our n hat ds and then actually do the surface integral with this one. Okay, well, let's go ahead and do our curl. Watch out for that. I fell into that trap, so make sure you don't fall into that trap. Be sure to read carefully what we're actually including as part of our surface right here. All right. Let's see here. So we have partial x, partial y, partial z. Wait, what question is this? Z is greater than or equal to 0 there just for the kicks? Oh no, it's because if we didn't include that, then this could have kept going downwards forever here. So this is kind of just stopping it from going on down forever right here. If they wanted to include the disk, they also would have said that if they wanted to include the disk, here's how they would have written it. They would have said this for z greater than 0, and then for z equals 0, they would have said that x squared plus y squared is less than or equal to 4. If they would have added that part as well, that would have included the disk right here. All right, let's get, do we really even have time to do this? How about we just pick this one up next time? This is going to take a little bit more work to do, and I don't want to keep you guys over here. But yeah, we'll pick up on number 11 next time, and then we'll get all the way through question 20 right here. All right, so that's it for today. So I will see you guys Wednesday, where we will have our conclusion for this exam.